Moving into Chapter 9, the big difference between Chapter 9 and Chapter 8 is in Chapter 9 we're going to be dealing with two populations. We'll have two different samples, perhaps from two different populations, perhaps from the same population. Kind of depends. And we're going to want to make statistical tests on the same kinds of things. So we'll start out in section 9.2, making statistical tests on whether or not two proportions are equal. Now you might notice a little difference between the null hypothesis here and the null hypothesis from chapter 8. Here it's P1 equals P2, for instance. And it's not, there's other variations on that. But basically, the proportion from one population equals the proportion from another population. Whereas in chapter 8, it was the proportion is some specific value. So in chapter 8, you only had one sample to deal with, or one population. Now we're moving into something that has two populations. And a big thing that you'll be tested on is being able to recognize, well, what do you have? And setting that up correctly. Now that handout I've given you has been updated a little bit. I've been spending a lot of time trying to update my handouts. It still has the same basic 6 steps. It's just that I'm starting to put in some stuff for StatDisk. Start out by stating your null and alternative hypothesis. I guess before then, you really should verify that your assumptions are met, and that is the number of successes and number of failures is at least 5 for each sample. So at least 5 successes, at least 5 failures for each sample. Assuming that's true, move on and set up your null and alternative hypothesis. If you're doing this old school, you would find the critical values from the Z distribution. And I see one little typo that I got to correct here. That's going to be an H sub 0 on both of these. You know what? No, it doesn't. I'm sorry. I thought I was wrong, but I was merely mistaken. That is HA. The tail on these tests depends on the alternative hypothesis. So we're okay there. If you're doing it with StatDisk, go to Analysis, Hypothesis Test, and then Proportion to Sample is what you want to hit here. Choose the level of significance, and then enter in your summary statistics. If you're doing it with StatDisk, instead of step 4, computing this awful calculation here, you're going to find the p-value. And if the p-value is too low, H0 must go. If it's lower than the significance level, you're going to be rejecting the alternative, or rejecting the null hypothesis. So that'd be step 5, and then state your conclusion in words. If you're stuck doing this by hand, here's how you set up your confidence interval. And it would be by referring to a Z. Fortunately, we don't have to do this one by hand, so let's do problem number 8 to begin with. You hear all kinds of these commercials recommending this herb or this supplement to treat this condition. So let's take an in-depth look at ginkgo biloba, commonly used as a treatment to prevent dementia. In a study of the effectiveness of this treatment, 1,545 elderly adults were given ginkgo, 1,524 were given a placebo. Among those in the ginkgo treatment group, 246 later developed dementia. Among those in the placebo group, 277 later developed dementia. Use the 1% significance level to test the claim that ginkgo is effective in preserving or preventing dementia. So we need to do a hypothesis test, and then we'll also look at the confidence interval. So let me give you a few of the summary statistics from this. So for problem number 8, the first group, the ginkgo group, we had N, I'll call it N sub G. was 1,545, and among those, 246 later developed dementia. By the way, do you know what a placebo is? Yeah, it's fake. It's like a sugar pill. And the reason they do that is because they want to, simulate giving them something, and sometimes there's psychological effects. You think you're going to be well, maybe you will be well, etc. So they're trying to eliminate a source of error, and they want to just say, okay, the only difference between these two groups is one got the ginkgo and one got the placebo. All right, so N sub P was 1,524, and X sub P was 277. We're going to test this at the 1% significance level. Now, it wants us to test the claim that ginkgo is effective in preventing dementia. Let's see. Now, if that's true, what's that saying about the proportion of those getting dementia that got ginkgo compared to the proportion of those getting dementia that got the placebo? Lower. Good. That should be lower. Now, it's something you got to kind of piece out carefully for yourself when you're looking at these things. So if this is effective, then the percentage of those people getting dementia taking ginkgo should be lower. So that has to be in our alternative hypothesis. So that's HA. Now the author and I differ a little bit, and it's just a matter of taste. It's not really a matter of substance. I think the author would put P sub G equals P sub P for the null hypothesis. I like it as a one or the other, so I like to put kind of the opposite there, putting it as greater than or equal to. In either case, both myself and the author agree that in the null hypothesis you have that possibility of equality. So if you wanted to put just an equal to or a greater than equal to, doesn't matter. Before I do my test, let's note that the number of successes and failures is at least 5 in each group. So you can probably think of the number of successes as the people who didn't get dementia as opposed to the ones that did. But in any case, that number is 246 or 1,545 minus 246. Both of them are greater than 5. So our assumptions are met. Assumptions. Let's put a little check mark there. And then turn over to stat disk on this one. So let's go to stat disk, down to hypothesis testing, and then proportion to samples. Now you have to be careful what data you put in what column. So in sample 1, let's see, well, let's put the significance level here, 0.01. Sample 1, we had 1,545, and 246 of those got dementia. In sample 2, we have 1,524, and 277 of them got dementia. We're not quite done here. We've got to adjust our alternative hypothesis. Which one of these do we want? 1, 2, or 3? 3. Because we want that P sub G is less than P sub P, or that P sub 1 is less than P sub 2. So I want this one. I think we're all set at this point. So let's evaluate. What's the information I need to get from this one? P-value. P-value. All right, so p-value. Good. Alicia, we got a p-value here of 0.0484. So what's that saying we're going to do with our null hypothesis given that alpha is 0.01? Nice. Fail to reject. Now, at the 5% significance level, if I was doing a test at the 5% significance level, what would my conclusion be? Reject. So it's kind of close. Depends on the severity of a type 1 error. Depends on, what are the consequences of rejecting H naught when it's true. Are they really bad? Then you want to make P naught or alpha pretty small. So in this case, thank you for the help. Fail to reject H sub 0. Our orange claim, all right, kidding. Our original claim is that P sub G is less than P sub P. That original claim does not contain the possibility of equality, and we failed to reject. Is that right? Failed to reject. So that puts us down here for the wording of our conclusion. There is not sufficient sample evidence to support the claim that ginkgo is effective in preventing dementia. Okay. Let's look at the confidence interval and see if the confidence interval is telling us the same thing. Now, the confidence interval is going to be the interval for the difference of those two. So what you're going to get is a confidence interval for P1 minus P2. Now, that confidence interval should contain 0. Because if 0 is in that, that means that these two are no different. So let's take a look back at the confidence interval. It does contain 0. So it's somewhere between 5.4% benefit and almost a 1%, ginkgo made it worse. It's somewhere in there is our confidence interval. So it's close to showing a little bit of a benefit, but that benefit looks to be more statistical than practical. I mean, if I'm going to spend a lifetime taking ginkgo biloba, I think I'd want more than, a 2 or 3 or 4% chance of avoiding, dementia. It doesn't seem like it's giving you that much of a benefit. So there's a difference between statistically significant and practically significant. And here, even if you did this test at the 5% level and you were able to reject, it still doesn't look like it's all that effective. Yes, sir?
Why is it at a 98% confidence interval?
Yeah, I've thought about that a little bit, and I think it's because you're putting that area in 2 tails as opposed to 1 tail. So our original test was a one-sided test, and it's not something that we get to see or we have to look at too much. Let me flip back here to this. When you're doing a one-sided test, you're putting all the area in 1 tail. So yeah, what they're doing, what it appears as though statistics is doing is saying, okay, we're going to take this value and give you a confidence interval. So that effectively means you need area in two tails. So that's why you're doubling that 1%. So yeah, that's what's happening there. Um, I'm sure you could calculate a 99% confidence interval if you wanted, but we don't have to. In fact, you know what? It's not a bad question. If we were to go up to analysis and then confidence intervals, we could do a confidence interval for two population or two proportion samples. I was hoping that it would import our last calculations. It didn't. So let's put in the numbers real quick. 1545, 246, and then 1577. 1524, 4, and 277. Do you want a 1? Do you want a, let's see, we'll do 99% confidence interval. Now what's going to happen, what you should have seen in your homework, is that if you want to be more confident, what happens to your confidence interval? Yeah, it gets wider. So this should be a little bit wider than our previous one. In fact, it is. So instead of 5.4%, it's 5.77%, and then a 1.2%. So it's a little bit wider as a 99% confidence interval. But, that makes sense. If you want to be more confident, you give yourself more room for error. Okay. So, yeah. No, good question. Appreciate it. All right. And again, this confidence interval contains 0. And if there's 0 difference between these, then we can't be rejecting H0. So, thank you. Okay. Anything else on this one? All right. Let's step outside the book and do one that's a little bit closer to home. Let's see here. Let's see if you. Okay, so does anyone want to go up to Flint and take a drink of water? Yeah, this it's a long time after it's supposedly been settled, but it's amazing that it happened in the first place, because we've known since Roman times. There's a letter that I found at this website that came out during the reign of Augustus Caesar that basically said, you know what, lead's not really a good thing. So they knew 2,000 years ago that lead wasn't a good thing, and yet somehow made it into the water system. Now there's a great program on Nova, I think it's called Poison Water, and I'll put a link to it on our website. It's about 50-some minutes long. It's really fascinating. It has a lot of great statistical issues in it. And let's see, here's the study. You can download it for yourself. It was written by somebody who worked in a hospital in Flint. But just all the different things that lead can do to you are just really, really bad stuff. What happens in the body is that lead has a kind of chemical signature of calcium. So wherever calcium can go, lead can go. And lead stays with you forever. You don't excrete it. It's just there. So it's bad, bad news. It's really sad that something like this happened. Here's the study that you can read on this. And I went through this and I pulled out some data on what happened to children. And what they did was they got blood lead levels from babies before the switch to water from the Flint River and after. So the before and after, and they kind of matched them. So let me summarize that data for you here and talk about it. Now, they regard a high blood lead level as being more than 5 micrograms per deciliter. So that's kind of their cutoff. And we'll just write example because we're doing our own example. We'll call it N sub pre. They had 736 samples that they looked at of blood lead levels before the water crisis. And X sub pre, let's see, it was 2.5, was 18 of those kids, I don't need to add another E here, 18 of those kids had high blood levels of lead. Now, post, and I have to notice that this number is really, really close. I can't help but think it's not accidental. 737 blood samples tested post changeover in the water source, and X sub post is 36. Let's test, and it's up to you how you would want to do this test. There are some people that would argue you should always test a two-tail test. That is, test whether something's equal or not equal to. That is, you shouldn't try and bias it one way or another. So let's go with that recommendation. H sub O, that the proportion of children with high blood levels of lead is the same pre and post changeover in the water source. So pre, post, and H sub 0, pre and post are different. Now, what level do you want to test this at? This is our own little thing here. So what significance level do you want to test it at? 0.01? Okay, sure, let's test it at 0.01. Alpha equals 0.01. Let's see here. Well, we've got more than 5 successes and failures, so we're okay with our assumptions. Let's test this claim. So we'll go over to stat disk. Get rid of this. Go back to analysis. Hypothesis testing. Proportion 2 samples. Now, one of the things that you've got to get comfortable with is deciding, is this a 1 population test or a 2 population test? Since we've got 2 samples, we're testing 2 different populations, pre and post, and seeing if the lead levels pre and post are the same. We'll make that test at the 1% significance level. Our alternative hypothesis is set correctly, but it's a not equal to test. Sample 1 was 736 individuals, out of which 18 had lead, or high lead levels in their blood. And then post was 36. I think we've got everything we need here. Ooh, interesting. All right, so our p-value is 0.0128. Now that brings up a great little talking point here. The p-value is 0.0128. Now, would you reject or fail to reject? Fail to reject, right? Yeah. But that's at a pretty high standard of the 1% significance level. Now, if you're the Department of Environmental Quality or Department of Water Quality, are you just going to wash your hands and say, okay, hey, we failed to reject? I mean, Statistically, you are sound. At the 1% significance level, you are absolutely correct in failing to reject. But is that the end of the story here? I mean, you're 0.0128. What would you do? Nothing. People got indicted for doing nothing on this. You shouldn't do nothing. Charles?
The risk is too great for the kids.
Yeah. Now, this is a case where the consequences of a type 1 error are really high. If you're saying, gee, we failed to reject at the 1% level, I mean, the consequences of being wrong are you're saying that, oh, the water's fine, drink it. I mean, really? It just boggles my mind. I mean, gosh, it'd be awful to see that coming out of your tap. People would freak out. I'm sure they did. 12 people died out of Legionnaire's disease that was probably born through those pipes. Wow, 90 people were, sent to the hospital, and tons of kids are going to face a lifetime of problems because they had high lead exposures. Now, the consequences of a type 1 error here are really real, and you have to be careful about your decision here. So at the 1% level, yeah, you'd fail to reject. Now, the study did talk about some limits of the study in their write-up here. One thing they said is that, look, we can't control the source of the lead. A lot of it's in old paint. There's a lot of old buildings that have lead paint. It was the United States was remarkably slow in removing lead from our products. So they can't really say what the source is. And I guess one criticism that I would venture is that, at least in my scanning of the articles, I didn't see them give the p-value. In fact, what they did do, though, was they said, oh, it's significant, at the 5% level. Well, give me the p-value so that I can make my own decisions and own judgments on this. I mean, yeah, it is significant, and they are right to reject it. It's a good paper. There's no doubt about it. And it helped finally galvanize people into action. But it took way too long. So, yeah, it'd be reluctant that I'd have to fail to reject here. But I'd put a lot of caveats in my notes about that. I'd say, look, I know we failed to reject, but, that's at a pretty high level of standard, a 1% significance level. So, yeah, fail to reject. Reject at H naught at alpha equal 0.01. But you could reject H naught at alpha equals 0.05. And like I said, what you should do is examine the consequences of a type 1 error and be really, really careful. I mean, at the very least, this would warrant more study, is what's going on there. Yeah, you could reject it at 0.02 or 0.015. So these are pretty significant results, and I think you can see that based on the p-value. You just can't reject it at the 1% level. That's still, it's definitely something that should catch people's attention. I think this study in particular, they really did. The actual author of the study was criticized for a while. I forget which officials were criticizing her, but they're saying, oh, well, you're spreading alarm unnecessarily. Not really. All right, would you like to do another two population proportion test? Or are you comfortable with those? Do one more? Okay. All right. Okay, so back to the book then for problem number 12. In a randomized controlled trial in Kenya, insecticide treated bed nets were tested as a way to reduce malaria. Among 343 infants using bed nets, 15 developed malaria. Among 294 infants not using bed nets, 27 developed malaria. Use a 1% significance level to test the claim that the incidence of malaria is lower for infants using bed nets. Okay, so let's write down some summary statistics for ourselves and look at making a hypothesis test. So bed nets, our population was, call it N sub B, was 343, and X sub B was 15. No bed nets, N sub N. N sub N was 294, and X sub N was 27. So regardless of how you define it, there's at least 5 successes and 5 failures in each group. So our assumptions are met. 5 successes and 5 failures in each group. We're going to make this test at the 1% significance level. Now, if bed nets are effective, then what should be my null and alternative hypothesis? Perfect. P sub B is less than P sub N. So P sub B is greater than or equal to P sub N. Or you could just put equal to. That's fine. Either way is fine. Okay, let's do this in StatDisk. Now I'm just going to edit the stuff that I already have here. I think you're comfortable with getting this. This is analysis, hypothesis test, and then 2 proportion 2 samples. This time we want 343 in sample 1, and 15 got malaria, 294 and 27 got malaria. 1% significance level. Oh, there's one thing that I got to change here first. The alternative hypothesis. And that should be that our first sample, P sub B, is less than P sub N. Okay. I think we're all set here. And that does change things a little bit. So our p-value is 0.0074. Okay. Charlotte, what's that saying we should do about our test? Yeah, reject H naught. So reject H naught. Good. Let's see if we can't word our claim. The original claim was which one of these? This one, wasn't it? We wanted to test the claim that the incident malaria is lower for infants using bed nets. So that's this one. That's our original claim. the original claim does not contain the possibility of equality, and we rejected H naught. So sample data support the claim that the proportion of those getting malaria with bed nets is less than the proportion of those getting malaria without bed nets, or basically that bed nets are effective. Sample data support the claim that bed nets are effective. Which is a nice short way of saying that the proportion of those getting malaria using a bed net is less than the proportion of the area of those getting malaria without a bed net. For homework, section 9.2, try problems 1 through 15.